Stefano, maybe we can start.
Okay. Okay, so let's start the second lecture. I just recall briefly what was the topic yesterday. So essentially it was a warm-up lecture where I was discussing some main features of long-range interactions in the feature of extensivity, the feature of additivity, and also I introduced a model, the Ising model in one dimension with long-range interactions, for which unfortunately there is no exact solution, but can be analyzed with approximate tools. And in the mean field limit, this model can be completely analyzed, and I showed yesterday that even if the interaction is non-mean field, so it's the case with distance, but weakly, the solution of the model stay close to the one-dimensional Ising model in the mean field Curie-Weiss limit. Then during the tutorial, I asked the students to do two exercises. The first one was to show ensemble equivalence for the Curie-Weiss model. And the second one was a discussion exactly of this long-range Ising model concerning the formation of droplets in the model. So I hope that the students were able to cope with the task, and maybe I will further discuss this issue during the tutorial of today. Oops, as usual, there is a problem with sharing the document. I have to share it again, I suppose. Yes. Okay. So today we will more go into the hot topics by showing the solution in the phase diagram of two mean field models, the Blume-Capel model and the Nagel-Kardar model. And I will discuss several features of this model, including the feature of broken ergodicity that I mentioned yesterday. So the fact that the space of in this case the plane of accessible states might not be non-convex, and also I will briefly discuss also the issue of metastability in mean field model, in particular the presence of exponentially long in the size time scales in the model, and then I will present a method which is very powerful and allows to get the microcanonical entropy from the free energy, and it works only in certain conditions, but it's a viable method to get the microcanonical entropy, so to establish or not the presence of ensemble inequivalence. Okay, in the tutorial, I will discuss briefly the transfer matrix method in relation with the Kardar-Nagel model. In particular, how the min-max method, that is the method that I was just mentioning, can be combined with the transfer matrix in order to solve in a different way from the counting of the Kardar-Nagel model. Then in the tutorial also I will discuss a little bit more deeply than what have been done in the literature, how to count states in the Kardar-Nagel model. And finally, I will present more with some more detail the Kreutz algorithm to simulate the microcanonical ensemble. Maybe it's too much meat for half an hour, or 45 minutes, but I think that the tutorial is, even if I'm not able to cover everything, I will put it in a sort of a stimulus for the students that they will then have to work out the solutions. So, okay, so let's start with the last slide that I should have shown yesterday, but was not shown, the fact that the entropy can be non-concave in the microcanonical ensemble. So you see here a picture of a typical, let's say, situation in which the entropy grows with energy. This is not always true. As you know, there are systems with negative temperature. And eventually, after the entropy has grown to reach this value, for instance, you could see my pointer perhaps on the slide, maybe it goes down with the energy. But let's not analyze this negative temperature part of the entropy. Let us limit us to cases in which the entropy grows with energy. This, by the way, is essentially true. So true without exception, with some exception, in systems where there is kinetic energy. So if you have a system of particles and you have kinetic energy, standard, I would say, kinetic energy, so quadratic kinetic energy, there will be the volume will grow as you increase the energy. Even if the energy does not go into potential energy, it goes into kinetic energy, so the volume will increase, and so it's very natural to expect that the entropy will increase with energy. So you see here there are several values of epsilon that are put in the abscissa. You see epsilon 1 and so on, epsilon h, epsilon. All these are names for positions of the energy, of the entropy, that are specific, so that are peculiar. So for instance, you see that between the first two values of epsilon, the entropy maintains its concavity. So if the entropy maintains its concavity, it means that the specific heat will be positive, okay? Because the specific heat, as I recall below, is related to the concavity of the entropy. You see here the formula in the microcanonical ensemble. The second derivative of the entropy with respect to energy is minus the inverse of the specific heat times the temperature square times the microcanonical temperature square. So you can see that since in the formula for the concavity, only the square of the temperature appears, irrespective of the sign of the temperature, so since you have t square, the concavity will be determined by the sign of the specific heat. So then you see a region starting from these values of epsilon and going up to the value, to these values of value of epsilon, in which the concavity is instead positive. So since the concavity is positive, then the specificity is negative. This region would be unstable in the canonical ensemble. So if you prepare a state lying on this part, in this region of energy, the canonical ensemble would give unstable states. And of course, there is another region which is asymmetric, which is on the other side, where the entropy is again with the negative concavity, so the specificity is positive. The two regions where the which enter in this that would be called a globally convex intruder, are then divided into 3 regions. Let's say, suppose you are now in a liquid state here on the left, and you are in a gas state here on the right. So you will, if you go down in energy, you will be in a metastable region first, in which you will have a supersaturated gas, so there will be sort of metastable. And then you go to the unstable region, where the entropy is convex, and then you go again into a metastable region before you enter the liquid region here at smaller energies. All that will be completely wiped out in the canonical ensemble and by the construction that I showed you yesterday. So if you perform the inverse Legendre-Fenchel transform for starting from the entropy, you get an entropy which should be called more properly the canonical entropy, that is essentially obtained from this entropy, which you can see as a structure which is much more complicated, to an entropy that is obtained by approximating, by let's say, by adding a touching line that essentially touches these two boundary points. Okay, so all the states that are here in the microcanonical ensemble will be described in the canonical ensemble by the states with the same inverse temperature beta t that are expressed in the bounded line. So this is equivalent to the Maxwell construction that I show here to the right, where you see that instead of plotting the temperature, I plot the inverse temperature. So as energy increases, inverse temperature goes down. And then you see that this beta t corresponds exactly to the equal area construction of Maxwell, which in fact you obtain by equating the two free energies at the two boundary energies epsilon1 and epsilon2, as it is shown here. So if you equate, following Gibbs' rule, the two free energies at the two boundary states, then you get easily this integral, which is in fact the expression of the equal area construction of Maxwell. Okay, so essentially in the canonical ensemble, you will observe the temperature, the inverse temperature that goes down, that it flattens out at the inverse temperature of the transition, which would be first order in this case, and then again the inverse temperature decreases again after this coexistence region. While in the microcanonical ensemble, you will observe the full S-shaped curve, where the metastable states that are present in the canonical ensemble are the states at the boundary, while the unstable region will be the one where the entropy, the inverse temperature increases with the energy, which means that temperature decreases with energy. So this is this type of plot was observed long before I started the investigation of spin system in gravitational systems. In fact, in gravitational systems, in spin systems, it will be slightly more complicated because in general, when you have symmetry breaking, which is a something that not often occurs in self-gravitating system. The two branches of the entropy, the branch of the entropy at large energy and the branch of the entropy at small energy might be different. So in fact, there could be non-analyticities of the entropy function at some value of the energy. You will see that this happens already in the models that I will discuss today. But in a true bona fide self-gravitating system, you would also observe this type of situation where the entropy is indeed smooth in energy. Okay.
Stefano, so one
Yes.
one question. So I mean, if I am doing the canonical thing, then that means the physical system, as I change the temperature, then at some temperature it will kind of phase segregate into a high energy and a low energy phase. Is that right?
Sure. If I am in the canonical ensemble, the states that are here, can you see my pointer? I hope that says that are in the flat region. There will be mixed states of the left state and of the right state. So it will be a mixture of the state with energy epsilon 1 and the state with energy epsilon 2, with a negligible, in a finite system, contribution of the surface energy. While in the microcanonical ensemble, you can really follow all of the curve.
Okay.
Okay. So, but we can discuss this in more detail if you want. Okay, so this was the first model. Then we, of course, once we understood how it was possible to solve this type of models, we solved many, and we are still working on finding several of these solvable models. So this is the Blume-Capel model. Is a simplified version of the Bloom-Emery-Griffiths model that was introduced slightly later. It's a spin-1 model where you have the usual Curie-Weiss term here, but with spin-1. So this term can also take the value 0 if the spins are 0. And then you have a term which is proportional to SI square, which of course is always positive, irrespective whether the spin is plus or minus, but it is 0 if the spin is 0. So this term, since delta is positive, will tend to encourage spin 0. So so there is a competition, okay, between having a random state and a state where at low energy the system displays a magnetic, the only ordered parameter, because of course you can make the magnetization by taking the difference of the plus spins to the minus spins and normalizing by the total number of spins, where the total number of spins is the sum of the pluses and the minuses plus the 0, but it can also take what is called in the jargon of the model that was used as a mimicking model for superfluidity in the 70s, the quadrupolar moment Q, which is the sum of the plus and the minus spins. Now, at the transition, both order parameter change coherently. So in order to distinguish the role of the two order parameters, you should add more terms to the Hamiltonian, but I will not do it in this case, simpler case, because it's not necessary to discuss ensemble inequivalence. So the free energy of this model was computed long ago by Blume-Capel, and it displays a line of, I will show, let me see, yes. Okay, let me give to this slide and go to this slide and then go to. So there are indeed two parameters in the model, but of course you can count, you can measure energy in units of J of the ferromagnetic content parameter. So you can put J to 1 if you measure energy in terms of the ferromagnetic coupling. Then there is the parameter delta, and then there is temperature, of course, and energy in the case of microcanonicals. So for the case of the canonical ensemble, then you have two axes. You have an axis, a delta axis, and you have the temperature axis, the vertical axis. I'm sorry here the T was cut. But this is the temperature axis. So suppose you are at delta equals 0. Then you will have at delta equals 0, you will have the Curie Weiss, okay? But with spin 1. So if you do Curie Weiss with spin 1, you obtain a slightly different consistency equation. I displayed it here below in this slide. You have to solve a slightly different, it's not the usual one with hyperbolic tangent, but it's simple to solve, and you get a second order phase transition at the temperature 2/3, okay? Then 2/3. Then if you increase delta, the transition remains second order in this plane until you reach a tricritical point, of which I will show you the location. It's exactly calculable. And then you have a first order phase transition, which has a line, which has a shape which first bends to the right, as I look it, and then it's quite sharply vertical here and reaches the this state, this value 1/2. The value 1/2 is easy to compute. I suggest it also to the students as an exercise. You just compare, since you are at 0 temperature, you can just compare the state with 0 magnetization, the state with magnetization 1, and you compare the two energies, and you see when the parameters are such that you go from this ground state, where the magnetization is 1, to the other ground state where the magnetization is 0. And so you can easily compute by comparing the energies, this value 1/2. So you see that the phase plane is divided in two parts. One part where the magnetization is different from 0, and another part in which the magnetization is 0. And as you cross this line, which is second order here, then the tricritical point here, and first order here, you go from non-zero magnetization state to 0 magnetization state. The same happens for the quadrupolar moment. So the quadrupolar moment is continuously going to 0 along this line, while it goes to 0 with a jump when you are in the region of first order phase transition. Everything is calculable. So you see, for instance, the tricritical point is located at delta over J, which is log 4/3, with a temperature which is 1/3. Okay, so everything is calculable in the. What happens essentially is the usual picture. So if you plot the Landau free energy as a function, so yesterday in the tutorial I showed how to get the Landau free energy for the Curie Weiss. So essentially you use the Gaussian transformation for this term, no? So then you introduce an auxiliary variable, which I call x here, which is the Landau order parameter. So if I plot the free energy as a function of both beta and x, x is not the magnetization, it's the magnetization is obtained by solving the consistency equation in X. So you go at high temperature. If you are in the region of second order phase transition, you have a single minimum in the free energy located at 0. And then, like in the Curie-Weiss model, there is the bending of the Landau free energy at this point changes, and this point becomes from a minimum becomes a maximum, and so you have the continuous phase transition in X. While in the case of first order phase transition, before the transition occurs, two extra minima develops at finite values of X, and then these two extra minima becomes lower and lower until they reach the same height at the minimum at X equals 0, and then they become true minima with a jump in X. The jump in X reflects into a jump in the ordered parameter. So, for instance, the left panel shows the case of a second order phase transition for temperature 0.8, 0.63, and then 0.4. You are going to smaller and smaller energy at delta equal 0.1. Okay, so before the tricritical value. While the right panel shows the case of a first order phase transition at delta equal 0.485. So it's quite a narrow region. You have to play with the values of delta in this very small region here. And then you get this picture, which is the exact picture of the Landau free energy for this case. Delta equals 0.485. And this is temperature 0.5, then 0.24, where the two minima rise, two extra minima rise, and then 0.21, where the minima are more or less at the same height, and then the side minima are below the central minimum. So what you should expect in the canonical and microcanonical ensemble is exactly the same picture if you are able to plot the entropy. No? The entropy will be in some sense a reverted situation in which you have a maximum, which is the most probable value in m equals 0 and zero magnetization, and then you develop in the case of first order phase transition two extra minima in the extra maxima in the entropy that then become true maxima at some but how to get the entropy of the Blume-Capel model? So in fact, nowadays we have developed many different ways of getting the entropy, but okay, this is the original one. It's a simpler one that so we exploit the fact that in analogy with the Curie-Weiss model, yesterday I gave by the way, I gave the entropy of the Curie-Weiss with the wrong sign. I think the students realized. So
what is the dimensionality of this Blume-Capel model?
The dimensionality, you mean, okay, it's a mean field model. So there is no really space here, but you can imagine you are in one dimension. So you number the spins with a label 1, 2, 3, and so on, where the local label is as a meaning only for this spin, and then you have global coupling. So all spins are coupled to all spins. So there is no dimensional. So if you want in this model, there is only the mean field term and the local term.
Yeah, so the mean energy for this model can be calculated exactly.
What the mean energy?
Energy.
So of course, yes, can be calculated exactly, like for the Curie-Weiss. It can be calculated exactly. There are several ways you can do it. One way which the students can do by their own. I was too fast. is to write this term that I'm now circling with my pointer as a square, no? Then to apply a Hubbard-Sassonovic transformation to write a Gaussian integral, and then everything is local because you have the auxiliary variable x multiplied by the magnetization, which is local, and then you have SI square. Then you trace over the values of the spin, 0, plus and minus 1, and then you do saddle point and you get the free energy. This is a very simple exercise, but interesting, and the students can do it. And what you get this free energy of this shape, okay? This was done by Blume-Capel in the 70s. Now, in 2001, together with David Mukamel, we discuss for the first time this model in the microcanonical ensemble. So now just put questions if you don't understand, because maybe I'm skipping important issues. So a typical configuration of this model. So in this way, it recalls a little bit the one-dimensional setting, but I'm simply listing the spins from the left to the right. You see that there is a cluster of plus spins of 8 plus spins, and there is a cluster of minus spins, there is a cluster of 0, a cluster of minus, and so on. Okay. So how many configurations can you write given the number of plus spins, the number of minus spins, and the number of 0 spins? Of course, I can exchange any pair in this group and get a new configuration. So I can exchange a 0 with a plus and so on. And the energy will not change, because the energy is fixed by the number of plus spins, the number of minus spins, and the number of 0 spins. Because in the model, there is only a local energy term and the global mean field coupling. So any exchange of any pair will leave the energy unchanged. So I will remain on the energy shell by simply exchanging any pair of spins. But of course, I get the same configuration if I exchange the pluses with the pluses, the minus with the minuses, and the zeros with the zeros, because these particles are indistinguishable. So in order to get the volume, like I do usually for the Curie-Weiss model, I have to normalize n factorial, which is the number of exchanges of n objects, by n plus factorial, n minus factorial, and n 0 factorial. Is this clear to everybody, this counting? The standard counting that you do for the Curie-Weiss, but expanded to the Blume-Capel. Okay, so if there is no question, I think it's clear. No, it's a standard textbook calculation. Then I use for all these numbers, for all these n factorials, the Stirling approximation. The Stirling approximation is log n factorials equal n log n minus n. Okay. Now, what is the Boltzmann entropy for this model? The Boltzmann entropy is Kb log of omega. And I come to the question of Abhishek yesterday. So is the entropy scaling or not with n? One can check in this case explicitly that the entropy scales with n, as you can see in this formula, okay? But it's in some sense a necessary outcome of the fact that the entropy is a factorial, is a combinatorial quantity, so it cannot, due to the Stirling approximation, you can see that there is a scaling with n. Okay, so but the result is interesting because once I express, so I'm going back to the slides, you can see that here M is expressed, the magnetization is expressed in terms of the number of plus spins and the number of minus spins, okay? And the same with the quadrupolar moment. So I can express the number of plus, the number of minus, and the number of zeros as a function of M and Q, as I do in the Q-revise when I express the magnetization in terms of the number of pluses and minuses, okay? So what I get is this expression for the entropy, which is different from the one of the entropy. Here is the minus sign that I missed yesterday in the entropy for the Q-revise. So you can see that it has a more complicated expression in terms of M and Q. Now, if I look at the energy of the model, I can see that the energy can be expressed, energy per spin, can be expressed as a function of delta and of J. Here I have put, here is essentially SI squared term that gives rise to Q, and here is the SI SJ term, which gives rise to M squared. And this constant K is nothing but the ratio of J to do delta. So I have put the energy scale delta in front of the term here, Q minus Km squared. Okay, the reason will be clear in a while. I will use this variable, the ratio of the two terms, as a way of changing the way I cross the phase transition. No? Since you can see here from this plot that if delta is small with respect to J, to T, I am in a region of second order phase transition. So if the slope is high, I cross the phase transition line in a second order, in a region of second order phase transition. While if a slope is small, I cross it in the region of the first order phase transition. So I will use the parameter K. I will change the parameter K in order to cross the phase transition line in different regions. Okay. Okay, so what I do, I have here the entropy, which is expressed in terms of the global mean field parameter, so the magnetization and the quadrupolar moment. But I can use this expression to write Q, the quadrupolar moment, as a function of energy and of magnetization. Okay, so here, if I divide by delta, you see Q will be epsilon over delta plus Km squared. Okay, so then I replace Q in this expression, and I get a function of epsilon and M. This is my Landau entropy. So it's not the Landau free energy, it's the Landau entropy. So the entropy expressed as a function of energy and magnetization. Okay. Now, what I have to do in order to get equilibrium states, I have to maximize this entropy at fixed energy. So I have to find all the magnetization states, and among all, the ones that maximize the entropy. Okay, this is something that, okay, it's a complicated anyway expression. So, but anyway, what I did the first time was to do it numerically, and I then obtained the microcanonical entropy by taking the derivative of the entropy per particle with respect to the energy per particle. It is written here. Okay, this is not the canonical entropy. It is the microcanonical the microcanonical temperature. Okay, so then I go to this maybe complicated plot, but okay, it will take me 5 minutes to describe this plot. So in the each of the panels, we have 6 panels. I have a different value of delta over J. Okay. So I'm starting with a delta over J. I didn't even plot the region of a small delta in which the phase transition is second order, and I go directly to the value of the tricritical point. I will tell you later how I determine this. I have already told you how to determine this point. This is exactly the tricritical, the microcanonical tricritical point. It's the value of delta over J at which the transition changes from second order to first order in the canonical ensemble. And you see that there is an interesting feature of the entropy as a function of energy, that the entropy becomes flat at a certain energy. Okay, and then it changes completely to a linear behavior. The linear behavior because at this point the magnetization vanishes and the temperature, the microcanonical temperature normalized to J, it becomes linear in epsilon. It's sort of equipartition. Okay, but the interesting fact is that the temperature becomes flat. That's characteristic feature of the tricritical point. When you look it into the, it's unusual to plot temperature as a function of energy. So and that's why yesterday in the tutorial for the students, I asked them to plot this function, temperature as a function of energy for the Curie device, which usually is not done. And you see that there is a typical feature that dTd, so the derivative of temperature with respect to energy, is 0, which means that the specific heat diverges at this point. So when you are in the canonical ensemble at the tricritical point, what you get in the microcanonical ensemble is a diverging specific heat. So the specific heat diverges. This is the signature of the tricritical, of the canonical tricritical point in the microcanonical temperature energy diagram. Okay.
Question?
And then, yes.
So in the previous slide, so when you take derivative of S with E, then you get temperature as a function of E as well as M. How do you fix M?
I do it before. So I maximize, first I maximize at fixed epsilon with respect to M, okay? Fix epsilon and maximize S with respect to M. Then I get a value of M which maximizes S, okay? And then I have a function which is a function of epsilon with maximizing M, okay? Which is only a function of epsilon. And then I derive this function with respect to epsilon. It must be done in 2 steps.
Thank you.
Is it clear?
Thank you.
Okay. It's a bit tricky when you, of course, if you are in a region where the maximizing value of M is close to other maximizing values of M, it's easy to do this kind of procedure. You could even take the derivative with respect to epsilon, then look at the M which maximizes, but which maximizes S. But it becomes tricky if you are close to a transition, no? Because of course there are 2 regions, one where M is 0, the other where M is non-zero, so you should be careful in maximizing correctly the entropy. And as you can see, we were, unfortunately, this is a joke, we were not very lucky with David, because you can see that the range of temperature that is explored in this model is very small. So you see it goes from 0.332 to 0.334. So it's amazingly hard numerically to get a very precise graph of this kind. You have to go to quadruple precision and so on. But okay, this is just a remark. Fortunately enough, for other models, the range in temperature is higher. So we are relieved from this numerical problem. So then, if you vary delta of Lj, so you go towards larger values of delta, then you can see for the first time the negative specific heat. So here you see that the temperature increases up to this point, and then it decreases. So this is a region of negative specific heat. And then, of course, there is an energy at which you get a transition. It's a microcanonical transition. And then following, you have the equipartition region where the dependence is a straight line. Okay, as you further increase delta, so you go beyond, and you see that here the increase is really small, 2256, 2407. Then you get to a point where instead of having the temperature that flattens at a given energy, you have a temperature whose derivative becomes infinite with respect to minus infinite with respect to the energy. And this point didn't have a name in the literature, so we called it the microcanonical tricritical point. It's if you want, is the mirror point of this one. So instead of having a diverging specific heat, here you have a specific heat which vanishes at this point. So we called it the microcanonical tricritical point. By the way, such type of singularities were found in gravitational systems, and they had different names. So for us, it was very natural to call it microcanonical tricritical point. Then if you go beyond this point, then I fear that my plan of today will be disrupted, because I'm trying to go as slow as possible so that you understand the feature of this phase diagram. So you see that here, there is a gap here appearing in temperature, which is very similar to the gap that appears in energy, which is called latent heat, in the canonical ensemble. We could call it latent temperature in some sense. So I have a branch of states in which the specific heat is positive. Then I have a region where the specific heat is negative. You see that here the temperature decreases with energy. Then I have a jump in temperature, and then I have the equipartition region. The jump is always in the negative side. It can be proven. So there is also a decrease of temperature rather than an increase of temperature. An increase of temperature would be impossible due to some convexity property of the entropy. And then I have a region also the specific heat disappears, negative specific heat disappears, and I have only a jump in temperature. There was somewhat a discussion when we found such a jump, because you have to conceive situations in which at a given energy, the system has two temperatures. But if you realize that temperature is a derived quantity in the microcanonical ensemble, there is no mystery in this. Simply, the temperature as a sort of bimodal distribution when you are at this energy. And we have checked in some models the bimodal form of the distribution. So that when you are close to this point, one of the two peaks disappears, and when you are here, the other peak disappears. Okay, so you are perfectly in equilibrium, but you have the temperature is not well defined because you are in the microcanonical ensemble, and the temperature is a derived quantity. Okay, so I might stop 1 minute here to see if there are questions.
So, Stefano, in this, when you maximize the entropy as a function of m, so you get some, let's say, m star, so that so the system is actually magnetized at that values.
Yes, yes. The equilibrium value of the magnetization is that value at that given energy. At that given energy, yes. That's right. Then you do not know the temperature of that state. In order to know the temperature, you have to do a small shift in energy and see how much the entropy increases as you vary the energy. And then you get the temperature.
Okay, so the relation between temperature, magnetization, and energy, let's say, I mean, so if I could do it from the canonical ensemble, I would get a different relation. Is that right?
Yeah, yes. In our review, thank you for the question. I don't know, Abhishek. You are Abhishek?
Yeah.
Okay, thank you for the question. We have a series of papers. Some of them are written together with Ugo Touchet and others. I wrote with Shamik Gupta also, where we study this problem more broadly. So we study the full manifold, the manifold where you have temperature, energy, and magnetization. And the relations then are related. So the reason why you get ensemble inequivalence is that some of the Hessians that you have in such more complicated manifold have different properties in the canonical and canonical ensemble. So you can really study. So here the study was limited only to the point where you are close to an equilibrium state. But if you enlarge the picture and you go to the manifold of energy, temperature, and magnetization, of course, it's a more complicated manifold. It's a three-dimensional manifold. Then you get double derivatives. So you get the second derivative of the entropy with respect to and the mixed one, so the one that you derive once with respect to energy, with the other with respect to temperature. So it's an interesting exercise in the theory of functions. Are there other questions? Okay. So I have 40 minutes. I hope I can get to some point. Maybe I will be very brief with the Kardar-Nagel model because it's sort of similar. Okay, so you can also do Landau expansions, and this is here an example. So where I expand the microcanonical entropy as a function, of course, which is an even function in Emma, and I get the three coefficients of the expansion: the constant, which is a function of energy, the constant A, which is a function of the parameter of the system and of energy, which is here normalized to delta. So I measure the energy in units of delta, and then you get. As usual with the Landau expansions, you can get the line of second order phase transitions in the microcanonical ensemble by taking 0 the mass terminal. You impose at A equals 0 and you get the line, and you realize that the line is the same as in the canonical. This is totally independent calculation. So there is a physical principle behind this fact, okay? So I'm not computing the second order line using the result of the canonical ensemble. I am using only the microcanonical ensemble and computing the critical line. And the critical line is the same as the critical line. So I have not here the expression because it would be exactly the same. When I replace, of course, energy with temperature with the relation, when I use the relation between energy and temperature, I get the critical line of the canonical ensemble. So that led us to think that that we should not look for at least for the most important manifestation of ensemble inequivalence near second order phase transition, because at a second order phase transition, at least as for what concern, not for what concern critical exponents, but for what concern the location of the critical line, that is the same in the two ensembles. But what is different is the location of the tricritical point. So if I then impose that both A and B are 0, so I impose that the three terms of the development of the entropy are 0, of course, I would have to compute the C term in order to check that the C term is non-zero. Okay, and we have done, of course. And then I get the two expressions in the canonical and in the microcanonical phase diagram of the two tricritical points. And you can see that, again, this comes to my comment before, that the distance between the two is really very, very small, but it is there. So we are sure that we did it without mistakes, this calculation, and it's an analytical calculation. And this convinced us that although the 2 points are very, very close, they are distinct. And indeed, the picture is the following. The picture is the following. So this is, since the numbers are so close, this is, if you want, is a graphical picture of the situation. So I have here the KBT over J, the y-axis is the temperature, and in the x-axis I have delta over J, okay, the parameter of the Blume-Capel model divided by J. Now, this is the line of second order phase transition in the canonical ensemble, which coincides with the line of second order phase transition in the microcanonical ensemble. Then I meet the canonical tricritical point. Okay, at this point, the transition becomes first order in the canonical ensemble, and here I draw the first order line in the canonical ensemble, which ends with a steep region here, okay? But in the microcanonical ensemble, the line of second order phase transition continues beyond the canonical tricritical point and reaches the microcanonical tricritical point, the one where the specificity is 0, okay? This fact that the microcanonical tricritical point goes beyond can be proven theoretically. So we have a theorem that proves that it cannot be the opposite. So it cannot be that the microcanonical tricritical point comes before the canonical tricritical point. In equilibrium, this cannot happen. Then at this microcanonical tricritical point, the line of temperatures in the microcanonical ensembles splits in two lines because we have the upper and the lower temperature, the temperature jump that I was telling you. So at a given value of delta, there are two temperatures, the upper temperature and the lower temperature. And there are no states in the microcanonical ensemble in this region here, okay? While you can see that the line of first order phase transition of there are no temperatures, better to say, than in the canonical ensemble that have value in this fishy area. Then you have the line of first order phase transition that goes to the point, and you see that the two lines of the temperature jump in the microcanonical ensemble, they meet at the end point. This also can be proven. Okay, so this is essentially the result. So canonical and microcanonical tricritical points do not coincide. The microcanonical transition line splits in two lines at the microcanonical tricritical point, giving rise to a temperature jump. And the region between the two microcanonical lines is accessible only to metastable and unstable states in the microcanonical ensemble. And it's the equivalent of the coexistence region in the canonical ensemble. So I think this ends the description of this model. So I would like to stop again 1 minute to see if you have questions.
So the CTP and MTP, they are actually very close, right? That's what you showed in the previous.
Yes, yes, they are actually very, very close. They are not close. They are. It depends very much on the model. So in other models, we find that they are more far apart.
Okay.
In fact, this was I remember very well this because in the numerics that I had, since they are so close, it was really very hard to distinguish them, and it was necessary to do this Landau analysis expansion really to check that they are different. Okay, so if there are not other questions, I like to show a slide which is a nightmare slide. so this is comes from a paper that Freddy Boucher and Julien Barret. I would like just to show you just as a motivation also for understanding more complex situations. So it is possible by studying general properties of entropies and free energies and the relation with temperature to study many different types of bifurcations that can happen. And these are an attempt. This is an attempt of classifying all kinds of bifurcations. And what I can tell you very rapidly is that we have tried to find models that correspond to these type of different bifurcations. And we have found one with azeotropy, for instance, which is a sort of XY model with in an external field, which shows this kind of bifurcation. So just to motivate the fact that if one is interested, these are sort of singularities, or as Tom would like to call them, catastrophes, that correspond to different ways that phase transition can occur in the microcanonical ensemble. It's I have half an hour, so I will go very fast here on the Kardar-Nagel model. Maybe I will do something more in the tutorial. So, but just we wanted to understand whether this feature remains when the model has space. So this comes to the question before. So in this case, we have a one-dimensional model, and then we take the one-dimensional Ising model. Here you see the Hamiltonian of the one-dimensional Ising model, and we add the Curie-Weiss term. Now it's this model is has a space because we are in one dimension, and there is a mean field term. You add a mean field term. In order to count the states, we introduce the number of antiferromagnetic bonds, which is given by this big U here. I will give an exercise, the calculation of this omega here, giving some hints. So this you can see, if SI is equal to SI plus 1, this is 0, okay? This is non-zero and it's 1 only when you have an antiferromagnetic bond, no? So when you when you are in this situation. This is the antiferromagnetic bond, and you are going from plus to minus. And you also have an antiferromagnetic bond if you go from minus to plus, okay? Now you have to count the number of states. So, okay, this is a typical configuration where you have a string of pluses, a string of minus, plus. You don't have zeros here, but you have the bonds, no? So you given the number of pluses, the number of minuses, and the number of antiferromagnetic bonds, you can count the number of configurations. This prefactor of 2 was not present in the paper. So the paper, we did a slight mistake. So, and it's a very interesting problem in combinatorics to study exactly this quantity here. And I have unpublished the result where we computed this quantity for any kind of boundary conditions, free, open, and periodic. And here there are numbers, finite numbers that appear in this formula, and this is an approximate here because essentially if n plus and n minus and u are large, all formulas for different boundary conditions, they give the same result. The result that we published in PRL a long time ago is the one without the 2 in front, okay? But of course, log 2 divided by n is 0, so it doesn't influence the result, okay? So essentially, we have the entropy for this model. This model was solved in the canonical ensemble by Nagel-Kardar at the end of the beginning of the 80s. And now we have the entropy, which is here, okay? You can see the entropy in terms of the magnetization and the density of antiferromagnetic bonds, of, if you want, of defects, of the density of defects. It's an interesting entropy function. Again, there is a role played by another quantity. Not only magnetization plays a role, but you also have the number of walls, the number of defects. And if you express the magnetization as a function of energy and the number of, or the opposite, you express the number of defects as a function of energy and magnetization, then you get an entropy, same game, you get an entropy as a function of energy only, and then you derive with respect to energy, and you get the temperature, the microcanonical temperature. This is the plot of what happens in this model, the phase diagram. For the interesting region here is for negative k. You can already physically understand, guess that this is the interesting region, because in the region where the ferromagnetism imposed by the Curie-Weiss term is present, and K has the same sign, so it tends to encourage ferromagnetism, you will have ferromagnetic state. But interesting region is where locally you have an interaction which tend to break ferromagnetic clusters, no? So, and that's the region where K is negative, no? So the antiferromagnetic. So essentially you have global ferromagnetism and local antiferromagnetism. This is enough to change the picture. And you see, in fact, that for negative K, already in the canonical ensemble, you have a line of second order phase transition, which meets a canonical tricritical point. Here you see the distance is more large. It is from around 0.3 to around 0.35. Okay. Then in the microcanonical ensemble, the region of second order phase transition continues beyond the canonical tricritical point. And then, as for the Blume-Capel model, you have this fishy region where there is a temperature jump, while in the canonical ensemble, you have a line of first order phase transition, which ends at this point. Also, this point can be computed by doing a comparison between the ground state here and the ground state there. The ground state to the right is the ferromagnetic ground state, while the ground state to the left is the antiferromagnetic ground state. Because at 0 temperature, the ground state is antiferromagnetic on the left of this. So if K is negative enough, the local antiferromagnetics dominates, the local antiferromagnetism dominates over the global ferromagnetism at 0 temperature. So this is an analog, if you want, of a quantum phase transition. So there is a transition at zero temperature. And here you have a region of ferromagnetic region. Here you have paramagnetic region. And at all finite temperatures, there is no antiferromagnetism. This is not true in 2 dimensions. In fact, Kardar has also another very interesting paper in 2 dimensions where the situation is more complicated and you get also antiferromagnetism. But in 1 dimension, you don't get antiferromagnetism. And of course, as you can see, we have computed exactly by Landau expanding the value of K at which the model, there is a microcanonical tricritical point, and the value of K at which there is a canonical tricritical point. And you can see that here the difference is more sharp. It goes from 0.3459 to 0.317. So looking backward, I would have better chosen this model than the other one to do the analysis, because the numerics was awful with the previous model, while for this is much easier, because the 2 points are well distinct. In fact, we have models in which the distance is even more, so it can be of the order 1 in the scale of the measurements. Okay, so now comes the last topic of today for the last 15 minutes, which is, as I promised, and this I could have done the analysis in the Blume-Capel. In fact, we have done, but we have not published the analysis in the Blume-Capel. So in this model, it is possible to get bounds for the region of accessible states. So you can see here is for the Kardar-Nagel model. I exactly plot the region of energies here, vertical axis, and magnetization, where I have states. Okay, and you see that this is the gray region shown here. So there are no states here. And these bounds you get several different ways. Let us argue physically. So suppose I am in a positive magnetization state. So I am on this side, okay? Positive magnetization state. So it means that the number of pluses is larger than the number of minuses. But then, if I am in such region, the number of kinks, the number of antiferromagnetic bonds, is bounded by twice the number of minuses. Why? Because you can easily see that you cannot have more than this number, twice the number of minuses, antiferromagnetic bonds in the configuration, no? Because this configuration corresponds to having an isolated cluster of one single minus spin. And this is the only state which gives a number of walls of defects, which is twice the number of minus. So this, you get the bound for the number. So this n minus can be expressed as n minus the magnetization, the global magnetization. So you get a bound of magnetization, which is essentially this one. So the number of kinks should be less than 1 minus n. So this imposes a bound in the energy and magnetization. I leave to the students for the tutorial to compute. This is this bound here. This bound here corresponds to this. And of course, the number of kinks must be larger than 0. And this bounds also is the same of the Curie-Weiss bound. So epsilon should go more or less by like m squared. So the same for if I repeat the argument for negative magnetization state, I will get this bound. And this bound comes from the Curie-Weiss type of bound. So suppose now I put myself at an energy which is more or less here at this level. So I get states here in this range. Then I get states here. And then I get states there. Okay? So these states will be around magnetization 1. These states will be around magnetization 0. And these states will be around magnetization -1. Okay? So, but since in the middle at a fixed energy, I don't have any states, it will be impossible if I start the dynamics here to jump there. Of course, I could jump with a non-local dynamics. I invert, let's say, clusters of spins and I jump here. But by local dynamics, by local metropolis Monte Carlo dynamics, I will never reach this region here or this region there. We wanted to be sure, and we performed a simulation in 2 different cases. In the upper case, I'm above this region. I'm here. You might guess why I get these jumps among the straight in this microcanonical Monte Carlo simulation. The reason is that the fact that I am above this point does not mean that I don't have, I'm not in a region of, in a ferromagnetic region, because essentially one has to look not only at the states, but at the probability of the states. And the probability of the states will be described by entropy. And the entropy, in this case, has this form. So you see that the 0 has less probability than the pluses and the minuses. And in fact, you can see that in the simulation, the system tends to stay more around 0, then sometimes jumps to minus 0.5, sometimes it jumps to plus 0.5, okay, and there are regular jumps. But now, if I go in the region that I was describing to you, the one where the 3 regions are well separated, in the simulation, which is expressed by these gaps in the entropy, in the simulation, if I start around 0.5, I remain around 0.5. I explore this region. While if I start in the region around 0, I stay around 0. So there is a real breaking of ergodicity, and the phase space in M is not fully accessible when I go from a region to another. So this is the kind of breaking of ergodicity that I was describing in my first lecture. Now, we found this for this model, but then we looked back into the Blume-Capel model, and we found it also in the Blume-Capel model. So it's not a feature which is restricted to this model. And in fact, we find it also in XY models, 5-4 theories. So it's very general what we find here. In this case, what is nice is that we can really bound the regions by this type of arguments. Another way to argue is by looking at the entropy, which is interesting, because you can see that there are logarithms as usual in the entropy. So the argument of the logarithm cannot be negative. So for instance, you see here that u must be smaller than 1 minus m, no, in order to 1 minus m minus u to be positive, which is the bound that I got with that type of reasoning that I was showing before. So another alternative way to get the bounds is by looking at the expression for the entropy to those regions that are allowed in terms of the order parameters of the system. Okay, so this is for what concern, and I finish with metastability. You know from the theory of metastability of system with long-range interactions that you expect at the time to overcome free energy barrier increases with an exponential in n to the power d minus 1 over d in d dimensions. Since we are in field, one can expect that you get this bound in the limit in which the dimension goes to infinity, which is exponential n. Okay, so but this bound should be valid. This increase of the time. So I'm here is a metastable state. Is a stable state. I have to overcome a barrier of size delta. This is a free energy barrier. So the time should scale like exponential of n to the size of the barrier divided by kBt. And analogously, in the microcanonical ensemble should scale with the size of the entropy barrier to kb. No, this is the analogous scaling in the microcanonical. So we have several papers where we check both the canonical and the microcanonical. And in the cases in which we can compute delta S and delta F, it's really possible to get fits that the metastable state is the one A. So you see the exponential increase of the time scale. This is for the Blume-Capel model. And here, for instance, is another interesting fact that there is also a time of growth when you escape from an unstable state, which is logarithmic in the number of spins. You see here the scale is logarithmic. Instead, here the scale is logarithmic, so there is an increase. And I don't want to insist much on that, but we have in a paper a way of justifying this by using a phenomenological Fokker-Planck equation. We can justify the logarithmic scaling in the case of unstable states. Unstable states means you prepare your system on top here, and you want to know how long it takes to go to one of the wells. And it takes a logarithmic time to go in one of the wells. So this is numerical, but also we have a sort of phenomenological theory. I have no time to enter in that. So it's already very, very late. So I think I will not have time to explain the min-max. So I will conclude and leave 5 minutes for questions, discussions. So ensemble equivalence is a generic feature of system with long-range interaction. I've shown 2 models that have nothing to do with gravitational interaction. The interaction is non-singular. The model is defined on a lattice, so everything is okay. There is no gravitational instabilities and so on. Nevertheless, we have negative specific heat, and moreover, we have temperature jumps. After we discovered the temperature jumps, people working with gravitational phase transition, they looked back in their files, and they also found temperature jumps. There are nice papers by Pierre-Henri Chavanis and others and, on that topic. The phase diagram of the Blume-Capel model shows ensemble inequivalence. And this is not restricted to models with mean field interaction, because we have shown that if you add a local interaction or even a nearest neighbor interaction, ensemble remain inequivalent. And then the last topic was ergodicity breaking, and I think it concludes what I said yesterday, I promised to do today, to show both the ensemble inequivalence and this additional feature of ergodicity breaking in the models that we have discussed today. So it is 5 minutes to 2 or 4 minutes to 2. So I think we can have some sort of open discussion. I can stop sharing if you want.
So if one performs a numerical simulation, does one see these temperature jumps that the microcanonical phase diagram predicts?
Of course, the jump is smoothed because you are at finite n. So the jump is smoothed. I don't have. I don't know. I have a simulation done. So, but I don't know where I have the file now. But essentially, you see the jump, and the jump is smoothed. It's more interesting if you fix the energy of the simulation. For instance, if you do molecular dynamics, I've done it for a model similar to XY model where I can perform molecular dynamics. So I use a very good algorithm to conserve energy. So I can look at the temperature as a derived quantity. So the derivative of the entropy with respect to energy in a system with kinetic energy is nothing but the average kinetic energy. There is a famous formula by Lebowitz, Verlet, and others, which states this. So I can monitor the kinetic energy to get the temperature. And then what I see, if I am at fixed energy, I see a bimodal distribution of temperatures. This is what happens in this region. So that you have a sort of bimodal distribution, and when you cross the transition energy, you have one peak which is more pronounced at the higher energy, and as you cross in energy, the other peak goes up. So you have a probability distribution with two peaks, and as you cross the transition, one peak can become prevalent to the other. Yes, this is exactly what happens. I remember one of the person who pushed me very much to understand better what happens in this situation was Eddie Cohen, who was not convinced that it was possible to have two temperatures in a system at a given energy. And he was right, I mean, to doubt. I remember with a lot of emotion, Eddie, because he was really a very nice person. So, and he pushed me so much that I decided to understand even better. And I think when I gave to him this type of explanation, he was then finally convinced that that I was right. Because in fact, it's a very strange situation where now what happens, for instance, one could analyze what happens if you put the system in contact with an external bath. Now, suppose I am in a situation where the temperature is the upper temperature, and I put the system in contact with a bath where the temperature is a lower temperature. So I think it would be very interesting to study this problem because, of course, there is an instability because the system is prepared in a region of phase space where the upper temperature is more probable. So there are many situations to which you could think that are sort of interesting from the physical point of view. It's an extreme case, if you want, of negative specific heat, no? Because it's in some sense a latent temperature, no? There is a finite jump in temperature corresponding to an infinitesimal jump in energy, no?
So this, I mean, so you showed that the dynamics is can be described by some simple Fokker-Planck equation. So is that kind of exact in it? So this is single spin flip dynamics.
Yes. This is an attempt to write a Fokker-Planck equation in M, no, in the magnetization. So you imagine that there is a system which has a global magnetization, and then the variation of the magnetization is small, no? You are varying magnetization very. So what drives the change in magnetization is the entropy, or the free energy, if you want. So you write down a sort of Oerenberg model for evolution of the magnetization, and so the potential is given by the entropy or by the free energy, and so the drift term is of the Fokker-Planck is the energy of the free energy or the entropy, and then you have the diffusion term, and the diffusion term is there is an hypothesis that we do, which is also checked in numerics, that in long-range system, the diffusion constant goes to 0 as the number of particles goes to infinity. So the size of the diffusion constant is 1/n. Now, if you do this hypothesis, that the size of the diffusion constant is 1/n, you get the logarithmic scaling with n. So, and now with a student, with a PhD student, we are trying to verify this property, so that the diffusion is going to 0 in long range systems, in mean field systems. We took another model. We took the Turing model, and we are trying to also to get more precise derivations of this Fokker-Planck equation. Now, for the Turing model, we are using the energy. So we are trying to write a Fokker-Planck equation for the probability distribution of the energy at a given time t. And we have in the book of Zwanzig, this is done for a single particle, and we would like to expand these to many particles, and we have derived some results, and we hope that we will publish soon, which confirm this exponential growth, that we are able in some cases to get an estimate of the exponential growth, and also the logarithmic region in the unstable case. So we are still working on this problem.
Sorry, so my question was the microscopic dynamics is just single spin flip dynamics, right?
Yes.
And you are saying that phenomenologically it's you can kind of model it with the Fokker-Planck.
Yes,
for the
exactly. Yes,
okay.
Exactly. Phenomenologically, we think that we are able to model the probability of the evolution probability of the magnetization, which is a global order parameter, using these two simple ingredients. Use as a potential the entropy or the free energy, and put a diffusion term, which is 1/n. This is the phenomenological model that we are using. It's a bit rough. We don't have many justifications, but now we are working more and on that, and we are close to a derivation of this Fokker-Planck.
Okay. Okay, yeah, so I think maybe we break for coffee
half
and
an-
then
half an
half an
hour
hour,
of,
yeah.
of break, and then I will start with the tutorial with the students. Okay.
Okay, yeah, thanks. See you
Okay.
tomorrow.
Thanks everybody for listening. See you tomorrow.